Thank you for joining this session. I would first like to thank SEM Israel for giving HCL Technology this opportunity to present here. Today I'll be talking about some innovation trend and the changes in approach towards design of IOs. As you know, IOs being the tiny, the smallest part, some of the smallest parts of a complex IC design, but they are extremely crucial in the performance of this of the complex ICs. Let's look at the changing scenario today. At the processor speed, as you all know, is increasing, churning out incredible speed, a large amount of data. And then we have these shrinking technologies in the form of FinFET that kind of starts packaging more and more functions in a chip. The focus now shifts towards newer techniques of moving this data in and out of these devices. And this in IoT and automotive applications, there are more and more computation being done in a distributed manner, requiring more data to be moved around in the system. With the shrinking technology, starting say 16 nanometer down to 5 nanometer today, causing core voltage reduction, and that from about 1.2 volt down to about 0.6 volt today. The question is, will the I/O voltage also reduce? As a challenge to kind of meet the dynamic I/O performance range, and also the ESD and latch-up issues become harder to address with this lowering voltage, eventually leading to reliability issues. And if I look at specific domains in the IoT application, that requires wide variety of protocols from ZigBee to Wi-Fi to BLE, and wired protocols like RS-422, RS-232, and stuff like that, the demand is more for multi-protocol or programmable IOs. In automotive and a number of consumer electronic products we have seen also requires backward compatibility or rather programmable IOs that can also support legacy interfaces. So here I will describe some of the examples that we have kind of developed in customizing IOs for applications. So one of the examples that I first would like to take you through is a DDR combo IO. This is an IO which was as per standard ZX standard of DDR, DDR1, but it also has to perform as DDR3 and DDR3L. So this was done in 28 nanometer, and as you can see from DDR1 to DDR3L, the supply voltage changes varies from 2.6 volt to 1.35 volt, actually as low as 1.28 volt in DDR3L, whereas the frequency range that needs to be supported in this IO was 200 megahertz to 400 megahertz. As you know, in a design, we also, of course, need to kind of verify the impedance calibration for all these modes, the signal integrity that we had to do for 4-inch trace at 50 ohm characteristic impedance, and DDR IBs as a load at far end. We also had to test, also support the terminated and unterminated cases where the receiver could actually receive partial swing or full swing signals. And the driver linearity spec, the impedance linearity spec, that had to be customized in this case, where according to the ZX specs, where the nominal driver pull up and pull down comes from 40 ohms, that was standardized to 50 ohms here. And the challenges, as I said, apart from the multi-protocol, the IO devices available were 1.8 volt devices, where DDR1 actually asks for over voltage protected architecture, as the IO supply will go up to 2.6 volt. And DDR3L mode, the IO supply actually goes down to about 1.28 volt, and yet it has to support 400 megahertz frequency. And more programmability options and more parasitics that gets added, and that becomes a difficult challenge to kind of overcome. And reliability also, of course, it has to be taken care of. And as usual, the usual demand for lower possible area and power. So this is how we have addressed this by having two different paths for DDR1 and DDR3. This was accommodated like for 28 nanometer GPIO would have, what we have designed is 55 micron by 300 micron roughly. In this case, the combo IO with DDR1 and DDR3, this one actually the cell height was close to 600 micron by 55 micron. So, and the parasitics of course was difficult to manage, but then we had to achieve those. At the end, we actually met the specs of both DDR1 and DDR3 3L, and with a maximum duty cycle distortion of 100 plus minus 100 picoseconds, both in all these modes and both in transmitter and in the receiver. Yeah. And of course, all the usual aging simulations and EMI, ESD had to be done. This is yet another case of customization of I/O. We have a slew rate control I/O, which was supposed to be a programmable I/O, but then eventually we had to support we had to actually deliver two different I/Os. But apart from the slew rate control, what was added was the same I/O was supposed to deliver 18 up to 16 milliampere of current for driving LEDs. Yeah. So this is one other example where you combine two different functions. Of course, in LED mode, it does not care about the slew rate, and this was this I/O was supposed to be kind of designed. The same I/O was supposed to be designed for two different types of loads of a 2-foot cable, 70 ohm cable, and a 5-foot 70 ohm cable. Of course, the slew rates were different, and the frequencies were different. This was 24 megahertz. This was 8 megahertz. Yeah, and again the devices available were 1.8 volt. The device were stacked to protect over voltage reliability issues. And there was another issue here that the slew rate and PVT really spread. We had a lot of spread in the slew rate as across the PVT, and this variation had to be taken care, and we did that by bringing in the process compensation with the slew rate that was kind of managed with the polydigesters process that was tracked, and the compensation bits were used to adjust the slew rates. Okay. So this is how. This is a block diagram. I'm not going through it. This has a simplified block diagram of this I/O, and we eventually met the specification about driving this slew rate control I/O for two different kind of applications, and of course it had to be free of all the EM and the aging simulations, and all that was done as usual. This yet another example where we had to design the LVDS receiver at 16 nanometer FinFET, and these are the usual specs here. But then this I/O, apart from being an LVDS receiver I/O, this also had to support the differential voltage range of 2 volt peak to peak. That makes it compliant to LVPECL standard, and also this same I/O is supposed to drive a PCI Express reference clock at 100 megahertz, and that brings in a very tight control of jitter. So the jitter spec had to be extremely tight for making this a PCI Express reference clock. So you can see here three different functions kind of are being addressed in one single I/O, a standard LVDS receiver, along with the LVPECL standard, and also the PCI Express clock. So this is what I was talking about. This is the new requirement that is showing up, and a lot of engineers are kind of trying to design IOs in this format. Let us now talk about a few trends in the IC design that are happening today. And as you can see, a lot of these ICs are now being designed in something what is called multi-chip module, or MCM, where multiple dies are packed into the same IC. And these kind of designs, they require short distance but high speed communication between these dies. Yep. And if you can see in the left hand side, there's an example of an Ethernet switch ASIC. Bottom there is an AI ASIC that requires die-to-die communication apart from the other external interfaces like Ethernet or PCI Express, etc. Now, this kind of applications, they require the kind of throughput, the high throughput rate, a lot of reusability and innovation that comes in this domain that kind of overcomes the challenge of low power and extremely high speed. On top of that, there is also the flexibility in architecture that can support multiple orientation of the I/O in the say north-south and east-west to enable efficient floor planning. And of course, I have already talked about the programmable IOs and multiple protocol support IOs that I've already discussed. Yeah. So in the IO domain, there are these different various applications that are there, like say high-speed interconnect, sensor applications, test application. For example, the IOs in tester application need to support much higher margin, like in zeta margin, in comparison to the standard. Okay? And in case of sensor applications, there are these trends of utilizing serial parallel interfaces between the sensor and the SOC, making it simple to use and also the latencies that are involved in using the PHY IPs, that gets removed. Okay? There are also these AI and the IoT domain ICs that are being designed in multiple technologies, and here there is yet another kind of option for innovation, where the architecture, IO architecture, has to be modular and programmable. Yeah, and that will enable easy porting of these designs between different technologies. And in different use cases, like in say high performance computing and server ASICs, server SOCs that are approaching maximum reticle size, the Ethernet switches and networking SOCs that are also approaching maximum reticle size. And then there are these AI SoCs that has distributed memories to kind of support complex algorithm, and they require die-to-die I/O interfaces. They require LPDDR4, LPDDR5, HBM2, HBM3. So these opens up a lot of innovation, reusability, and flexibility in analog architecture design, and that is the key to the future. Let me quickly take you through a background of HCL as an organization, which is present in 45 countries, 149 or 150,000 engineers, close to $10 billion of revenue, and we are part of a group of HCL, which is called Engineering and R&D Services, which is about 28,000 people with 350 customer base. Is one of the largest independent global engineering R&D groups in the world. And Silicon and System Development Services, SSDS, is part of Engineering and R&D Services, ERS. This supports multiple verticals like aerospace, medical, automotive, networking, consumer, semiconductor, cloud storage, and industrial, is supported by these competencies which I have listed here. VLSI engineering is for one, but then there are also this product development, firmware development, the support services, and the test labs. And this group has more than 3,000 engineers with 100 plus customers and a global talent pool, a lot of them in India, of course. Then we are also there in the US and Europe and also in Israel. A quick look into the analog and mixed signal IC design services that we have. On the left hand side, you can see different domain competencies like power management, data converter, clock and analog modeling, high-speed interfaces, and next to that we have custom layout team, a very strong team of 350 plus analog layout engineers, very competent even in 5 nanometer and 7 nanometer layout design. We have IP choice, what we call a set of standard IPs that we own, and we are able to use them in different IC solutions that we provide to different customers. Apart from that, of course, we have foundation technology, having standard cell, I/O, memory, etc. And down below, here there are a little breakup of the analog design competencies here. The I/O interfaces, then we have RFIC design, power management, data converter, clocking that I mentioned about. One of the unique services that we provide and not a lot of companies in the VLSI service domain can provide this is the SPICE modeling capability. We have done about more than 500 models, SPICE models for devices for a lot of mixed signal IC design companies worldwide. On the technology side, we have wide experience in a lot of technology foundries that you can see here, from 0.35 micron technology down to 7 nanometer, 5 nanometer. Foundries like Global Foundries, TSMC, where we have excellent relationship, and SMIC, UMC, and a lot of other foundries that we have exposure to. One of the other distinguishing services that we provide is the post-silicon validation services, that we have expertise in a lot of interface validation that you can see here on the right hand side, a lot of standard interfaces there, and on the left hand side you can see the silicon tester with test program development, characterization of devices, failure analysis, etc. And on the FPGA we have a platform that we use for several projects. These are supported in an excellent lab facility that is built in India as a huge facility with a lot of sophisticated equipments. HCL has actually invested more than $50 million in building this infrastructure. A lot of experienced people, and you can do tests like ESD test, EMI, EMC, and whole lot of other tests that are required for productization. And I would like to end my presentation with a view of the semiconductor ecosystem that we have today and how we are placed in that scenario. If you look at this diagram, this has these 4 quadrants with the contract design services in one bottom right corner. We have the tools of the EDA on one side, we have the contract manufacturing, and we have the systems and product. The conventional the design services, we have IP as a service, or we have ASIC as a service, we have systems as a service. But then in HCL, we have the capability of complete VLSI design and is supported by firmware systems and product development and support services and test labs, etc., where we are in a unique position to help our customers who are quality and cost conscious customers to move up in this value chain, move up this axis in this direction. Yeah, so that is where we add value, and this is where we aspire to be. Thank you very much for your attention, and thanks again for giving us this opportunity to present in this forum.